Welcome back, everyone. I want to thank Ariana and Sanahi as well as ET staff for leading that breakout session. And I hope we have some schools that will be brave and come on up to the screen and talk to us. We have a few more popping over still. Awesome. Well, I'm going to hand this back over to Betsy, who will introduce two more of our fantastic ET college mentors and get us going with the Q&A wrap up.
Yes. Oh, I cannot wait to hear how everyone's designs went. Sounds like you had a really good breakout session. So if there's any students who would like to come forward and share your design right away, we would love to see it. It looks like maybe we've got some coming up. And I see Academy Charter School. Are you ready to come up and share your designs?
They're waving. Can you come talk to us? Is that where we have Jerry Dawes? Yeah.
Oh, awesome.
Yeah, we just did with Joanna.
Oh,
If you'd like
perfect.
another, if you'd like to spotlight another set of students, we can do that. Would
Okay.
you?
We
Yeah.
would love you to.
All right, sure. You want Jeremiah? I have
Come on, Jeremiah.
Jeremiah. All right, so let's showcase Jeremiah.
Hi, Jeremiah.
Good morning.
Let's see that design you got going on there.
All right, Jeremiah, if you can turn around and explain what you did,
All
and
right.
they'll have some questions for you.
And stuff done. So the first thing we tried doing was just doing the regular cardboard trick and putting it right here so it's able to walk it in the direction it is. That's the pretty basic and simple one. And then the next thing Then the next thing we tried doing was doing a little bit of this and putting the foam right here, so able to look a little more flashy and designy. And then the next thing we were going to do was do a little bit of this and then place it on top like that
Oh,
for a
nice.
little like a little hat, something like that. Then the next thing we were going to do is place it on the side like this, and then place it behind it this time, so it's able to still block it from the same direction and stuff like that. And so basically, and then after that, we got.
Yeah, tell us about your results. Which one of these
And
different
after
iterations?
that, we got 82.5 from that one. The regular cardboard trick, we managed to get 79.9 from that one. And then the side one, we got 79.6 from that one. So, is there any questions?
Yes, I think it is so awesome that you tested it in so many different ways. That was amazing. So of all of yours, it sounds like one of them was the winner. Which way would you, as the engineer, design it? Which one was the best one for you?
The best way, in my opinion, was this one where I had the top on this one. It managed to get 85.5.
Lower
Oh, no, I mean, not me. Oh, my bad. So the best one we got was the side one actually, which was the 69.6 for that one.
Yes, that is brilliant. And so you just showed us the gamut. The highest one, which is not doing any good sound canceling, and then the lowest one, which is doing the most. And so I love that you showed all of those different variations. Did you try it with just one layer of the acoustic panel, or did you always use both of them kind of folded over?
I used the both of the layers. I didn't use just one.
Gotcha. And did you ever, I see the bubbles, you have them kind of inside, like folded on each other. Did you ever fold the bubbles so they were on the outside?
On the outside.
So you see how your acoustic panel has kind of like these bumps on it? Did you ever try it with the bumps on the outside?
Oh no, I haven't.
Do you want to try it right now with us and see if it makes a difference?
Yeah, yeah.
Yeah, cool. Let's do it.
Battery.
This is like real-time engineering. You guys are awesome.
Big shout out to Academy Charter School at Uniondale.
Oh my, all right. We made our lowest that we managed to get was 65.5 in that
Yes.
one.
High five to you. What does that tell you about those acoustic panels?
That the sound waves are so basically when the sound goes off, the sound waves are getting bumped by it, and most basically it's gonna cause a lower sound than the higher one, which on this side, because it was a smooth angle, while this one was more bumpy, so it would equal less more than what I originally did. So
I love it. Super job. Annie or Morgan, do you have any questions you want to add to them?
I was just gonna, oh, go ahead, Morgan.
Oh, okay. I don't have any questions, but I just want to say great job. You did the engineering process perfectly. So you actually went through step by step and you did a bunch of iterations. So I think you did a really great work, and that you might be a future engineer.
I was
Well,
just gonna say,
we have a sound engineer in the making here at Charter High School in Uniondale.
I can see that.
His name is Jeremiah. Round of applause for Jeremiah, please.
yay.
Good job, Jeremiah and team.
Nice
Excellent.
work.
Thank you to ET's own Jerry Dawes.
Are there any other schools in our group today who kind of got inspired from this, want to share now? As you can see, it's nothing intimidating at all. But I don't know if Jerry, you guys want to prep another person if you guys have anyone else. But besides that, let's see if anyone's ready to share.
And if not, we can go ahead and introduce ourselves as well. You all know who I am and why I'm here and what I love about Annie and Morgan. So you got me as an aerospace engineer, but they have some really amazing backgrounds to share with you as well.
All right. Hi, everyone. My name is Morgan. I am a senior in civil engineering at Virginia Tech. I am kind of interested in a little bit of everything having to do with civil engineering, but my main focus is sustainable land development. So that is designing new neighborhoods sustainably so that they can be used for years to come. I'm also interested in stormwater management. So when there is a big rainstorm, making sure that all the water goes to the correct places and that it doesn't flood the streets and doesn't get contaminated. I'm also interested in water resources engineering. So that is just making sure that everybody has access to clean water as well. But here's my engineering timeline. So back in high school, I was actually part of a STEM program. And back then I was pretty interested in biomedical engineering. So I actually was able to clone DNA back in high school, which I think is really cool. And I actually did a whole research project on that back then. But that kind of showed me something that I do not want to do for my career. So then I applied to Virginia Tech and I got in to Virginia Tech, but they start everybody off as a general engineering student. So I had classmates with people who are now chemical engineers. I also had classes with people who are comp sci, people who are aerospace, and that just kind of allowed us to actually figure out what we wanted to do and what major we wanted to do, and just gave us a nice year of cushion. And then my sophomore year, I actually interned with a construction company. So I was able to go on site, see how on site works. I also studied abroad to look at bridges in Europe, and I joined the American Society of Civil Engineers and the Steel Bridge Design Team. Then my junior year, I interned more on the land development side. So I learned about that and saw, hey, maybe I want to do land development for my career, which I ended up wanting to do, and I really enjoyed it. But then I also traveled to nationals with Steelbridge. And then my senior year, I am now about to graduate with my bachelor's degree in civil engineering in May, but I am going to stay for my master's in sustainable land development. So that is really exciting, which is probably a completely different path than Annie ended up taking. And everybody has a lot of different paths with engineering.
I am getting some notes that we've got challenge prep ready. And thank you, Morgan, so much for introducing yourself. And Annie will come to you as soon as this design is tested for us.
Wow, this looks entirely different than our last group, but
Yeah.
I'm so intrigued.
Good morning, challenge prep.
Morning.
Good morning.
So start with,
So, well, first what we did, we kind of went around the school and got some materials. We got a pillow here, we got a bucket, and at first we started stuffing stuff in here to see if, the sound could
reduce just by
Yeah.
having it stuffed in the bucket.
Yeah, and then that didn't really work out. So what we did was use these. We took them out to the side and made like a curve with them, but we need to add more tape, and it worked.
The lowest we got was like 51.
51.
Yeah. So our baseline was about a 63 because we have like a little mini sound studio next door. And that's why we were going back and forth because they were doing their measurements in there so we could have a more controlled environment so that we would have like that same baseline throughout the experiments.
Oh, that's fantastic that you have that at your fingertips there. Yeah, it looks like you have something you wanted to add as well.
Yes, Anthony.
Yeah. That's the only way we did it so we can work this out.
Yeah, good job. Thank you, Anthony.
Fantastic, thank you. And I'm curious, so it looks like that's like a seat cushion, is that right?
Yes, ma'am. That's sheet fishing.
Awesome, okay, and so that's a nice absorptive material, just like your sound barriers with your acoustic panels. And you have it curved out, you said worked the best, is that right?
Yes, ma'am.
Yes.
Yes, and how were you supporting it curved out? Were you just kind of holding it with your hands or did you
See the
make
bucket.
a support structure?
So
Oh,
we
yeah.
added, for the cushions, we added strings, and the tape wasn't really working for the for these, so we just kind of had to hold it together.
Gotcha. And I love that you are using materials that you're finding around your school. This is such an important part of engineering these days is finding sustainable ways to build things, whether that be bridges, whether that be sound barriers, whether that be spacecraft, things that we can use from our environment that would otherwise not be as useful. So way to go on that one. Annie or Morgan, do you have any questions for this group?
I think you guys might have hinted at this, but was this your only design that you guys were able to test so far?
No. We
This
had
is
two
our
Oh,
second.
okay.
So I said,
Yes, ma'am. This is our second design.
Oh, okay. How was the first one different from this, and what was like the result difference?
so this design, it reduced the sound. The other design, it wasn't really as effective as much as this one.
Okay, and what did the other design kind of look like if you just describe it in words?
So basically, we had both the acoustic panels and the pillow inside of the bucket.
We kind of like made this. We kind of like flipped this and like stuffed it in there and just stuffed everything in. We thought it would.
Just stuff it all in.
Yeah, we thought it would work, but it didn't work that well. So we just.
You know, I think that'd be my first intuition too, but then you guys realize that perhaps the sound's also traveling like around the bucket, right?
Yeah.
That's really great. Morgan, do you have any other questions?
I just wanted to ask, what would you change about your design if you were to improve it further?
Well, we would change how where these would go and how they could stay in place.
And you said how they would stay in place. Would you use tape for that? Would you try using like
Yeah,
popsicle
we tried
sticks?
some masking tape and a stick to hold it together, but
Okay,
it didn't really work that well.
nice. Well, great work. Betsy, do you have any other comments?
No, this was just amazing. And I love, like I said, I love the fact that you guys were hunting through your school to find things that you could use. And this is such a unique design. So way to go, you guys. High five.
Always
Thank you so much.
Yeah, great work.
Right. Do we have any others ready to go? Okay, if not, oh, maybe we do. Let me see. All right, I'm not seeing anyone right at the camera, but if you have another group that's ready, just wave your hand or drop it in the chat and we'll be happy to spotlight you. I'm going to go ahead and turn it back over and let Annie introduce herself.
Hello, everybody. Super excited to be with you today. My name is Annie, as Betsy has mentioned. I'm currently a senior as well, studying at the University of Notre Dame. Different path than Morgan. I'm studying computer science and economics as a double major. And then I also recently picked up a minor in Chinese as well. And the next slide, I'll kind of go through my little engineering journey as well. So I graduated high school 2021, and in high school, rather than having like a STEM engineering focus, I thought I was going to be pre-med actually, and so I did a bunch of pre-med, extracurriculars, trying to amp up for med school potentially. But when it actually came to declaring my major, I realized that if I chose something like biology or chemistry, and I didn't particularly enjoy it, then it'd be very difficult for me to kind of pivot paths, right? At the same time, I've always enjoyed problem solving. I've enjoyed my STEM classes very generally. I've enjoyed like these kind of logic puzzles. And so after, considerable discussion with my parents, my peers, kind of thought about, trying out engineering as like a starting point, because if I don't like engineering, it's a lot easier to switch out of engineering than it is to switch into engineering. And that is a whole logistical thing that I can explain if anybody has questions about that. But so then I decided, let me try out computer science, you hear the job market's strong, I think that I'd enjoy it. You get both the practicality of it and the creativity side of it. So that's what I started out as. And I ended up realizing that in my schedule, I could pick up a second major as well for economics. So not really engineering, but just a secondary interest I had. And that kind of led me to think about, what am I going to do in my career? After my freshman year, I ended up interning more on that economics major side of things. So I worked at a finance company in New York City. And although, I loved New York City so much, personally, I realized that the finance world wasn't necessarily, my cup of tea, the culture I wanted. At least at that firm, or just very generally didn't exactly fit like my interests in a real career. The next summer, I ended up helping Engineering Tomorrow, which is the amazing company that is working with you guys today, develop some labs. So I did neural networks lab and machine learning labs, if you guys ever get a chance to handle those. That was super fun, just kind of creating things, being able to kind of work within a team and produce something that I think is really beneficial to many people like yourself. And then we can move to the next slide. So then further that, so last fall, when I was a junior, I actually studied abroad in London, which was a ton of fun. And if you guys have questions about study abroad, that entire process and journey, please feel free to, think of those questions. While I was there, though, I had the opportunity to intern at Mars Wrigley, which is, if you don't know, it's like the big candy company that owns Snickers and Twix and M&Ms and all. So ate a lot of chocolate that fall, and it was just amazing. But that was in marketing, so it's kind of just more of an exploratory route for myself. You'll notice my entire, I guess, like stick is just exploring a bunch of things, because even now, like not totally sure, which I'll get to, but that was super fun. And then this past summer, I was interning at a company called PwC, which is where I did tech consulting. That's a very large word for essentially helping companies integrate different technologies into their company. And if you guys have questions about what that kind of looks like, I can go into that as well. But I really enjoyed the experience. However, it kind of left me realizing that, I did want to do a little bit more hands-on technical work. And so therefore I re-recruited, and I ended up accepting a position at McDonald's, nonetheless, in Chicago, in their global technology rotational program, where I'll get to explore a bunch of different sides of tech as well. So even after these 4 years, after the high school deliberations, I still had, a lot more, I think, to explore before I kind of settle down into a more specific realm. So you don't feel like you have it all together. You can clearly see that, it doesn't matter as much as you might think, and everybody takes their own path. So with that being said, like, please think of any questions that you want to ask me or Morgan. You can ask it about this lab, but you can also maybe more so probably encourage you guys to ask about college, about engineering, our experiences, how do we pick anything, do anything, and really just hope to inspire you guys and help you guys in this very, very difficult journey. But yeah, I'll turn over to Betsy now.
Yes. So I actually have some questions that the students submitted ahead of time. And both of you have such a diverse background. So I think this applies to both of you. What types of courses should be taken in high school and college to pursue a career in acoustics or in engineering? This is from Academy for Software Engineering in New York.
Okay. I can go ahead and take this question. So I since I did that STEM program back in high school, I took a lot of AP level classes. So that is advanced placement. And basically, at the end of the year, you take a big exam. And then if you pass that exam or get a certain like level or score, I think three, four, or five, that's all of those are passing, you get college credit the from that exam. So I think that that's really valuable, just because it kind of gives you that course load of a college course for you to kind of train up for when you're in college, but also you're still in high school, so it's still kind of like a high school based class where your teacher is asking you like or reminding you, hey, you have homework due tomorrow, like make sure you do homework, make sure like you ask us questions, whereas in college it's a little bit more flexible. But I definitely recommend if you're interested in any kind of engineering, so like sound engineering, software engineering, taking math, and if you're really interested in one thing, kind of focus in on that. So I mentioned that I was pretty interested in biomedical engineering. So I took AP Bio, I took the class where I cloned DNA, and then I learned from both of those. I'm actually not interested in this, so I kind of pivoted from there.
Yeah, I'd also add that so although we say that you don't necessarily need to be good at math or science to be an engineer, which I do strongly still, want to emphasize, the reality is that within your first, especially like year or two of college and engineering, there are some fundamental courses that you need to take just in order to even get to like the more interesting project-based classes. And so those might look like calculus, they might look like chemistry, physics, depending on the school you go to, depending on the requirements, depending on the specific engineering field. So, with that being said, I think it's really if you have the interest, I would say in your later years of high school, if your school offers like any advanced like science classes or math classes, to take them, because number one, like let's say you took calc like AB or the equivalent of like a first semester of college in high school, right? If you go into college, then that should be an easy A for you. You already learned the information, and especially with a big transition to college, it is such a benefit to just have something, off your plate a little bit. Secondly, if you have the opportunity to test for AP or IB programs, or even take these classes at a local community college, which I highly encourage you to look into as well, you can potentially even get credit for college. So, for example, I took Calculus BC AP back in high school, and by testing high enough, I got a high enough score to skip Calc 1 and 2 at Notre Dame, which is massive. That's two entire classes that you have freed up now, and I'm gonna be real with you guys. I think the college classes are typically harder than the high school ones. So like I kind of lucked out on that. Um, so just from a logistical standpoint, if you're looking into engineering, that's the way you kind of want to go about it. You want to either get things out of the way or just learn it well enough so that it's easy A when you enter college. But aside from that, like I know not all schools are going to offer, those advanced courses, and nor do they do teach you at school as if you know nothing. So it's not like if I didn't take it, I'm screwed or something. You can look into different clubs, different extracurriculars, maybe in your town, city, online now, virtually so many things to kind of get yourself just a little bit maybe ahead in terms of either your interests or your skills when it comes to maybe like a math course or something. So those are the things that I'd recommend. But I know we have other questions to get to, so let's move on from there.
Yeah, that was great. So you also, both of you had mentioned some like hands-on learning, and I love Engineering Tomorrow for that hands-on learning aspect. The question from the students was, how has hands-on learning shaped your journey in engineering and prepared you for your upcoming careers?
Annie, do you want to take this one first, or should I?
Yeah, I can go first. I think although engineering, at school is I think more hands-on than maybe other careers, like especially once you've entered the years sophomore or junior year, you can kind of do your own thing, be a little more creative on homework assignments, etc. I don't think it's until you do actually work in like either a club setting or an internship setting to actually understand what engineering looks like, right? I think when you're doing class projects, a lot of times it's like, oh, like a 2, 3 week project or a semester long project, and there's kind of like a clear answer, kind of a pathway to get there, but that's a class setting, right? That you're meant to, I guess, like have this result at the end. Whereas in the real world, engineering projects are typically a lot longer. And so it's not until you're working, let's say, like with a club to design like the fastest rocket, for example, or the fastest like race car against other schools, that you actually really have to kind of go out of the box and like really apply what you've learned in class to um, figure out, what could logistically be the best. And even more than that, an internship, you're probably working on a project that is not going to be completed in 1 to 2 months, during your internship. It's probably going to take years, and you are just helping on a small aspect of that. But by doing that, you kind of see like how like different engineers work on small things, and they kind of come together in this larger form that actually, creates huge impact on the world. I would say my personal experience within classes, I think those for coding, like those are the more ones where I could be maybe more creative with things like designing my own website, and I think that definitely gives me an idea of like the type of creativity and impact I'd want to have in a career. However, it wasn't until like being in industry that like last summer, for example, I, helped out on a project that was 2, 3 years long, and like I'm not gonna see the culmination of that at the end, and I might in the real world you might get moved projects and stuff. So you kind of get to see the much more realistic industry side of it. So that's been my experience. But what about you, Mom?
So my experience has been a little different. So my sophomore year, I joined the Steel Bridge design team, and that is a year-long design project where we design and fabricate a 1/10 scale model steel bridge and bring it to competition. We load it up with about 2,500 pounds and see how much it deflects down. We also see how fast we can build it. And with that, I have had access to actual structural software. You can actually see some pictures of some of the bridges I designed with that structural software. And that software isn't really normally available to students. It's mainly just people use it in the industry. And again, like I got my hands on structural analysis software as a sophomore. This is before I took intro to structural engineering. So I was playing around with all this information, and I actually got that hands-on learning, and I learned a lot more about intro to structural engineering than I did when I actually took the class. But another different thing that I have had in school, so last semester I took my senior design class, and it was designing a petting zoo in Northern Virginia, which I think is really cool. But we did all of the underground utilities, so all of the sewer lines, all of the water lines. We made sure that the parking lot was level and that like cars wouldn't slide off of the parking lot. So we also made sure that the roads were all up to code. So I kind of had a mini project that normally, like if you had done that in an internship, like Annie said, it would take years to do. Whereas my senior design class, we kind of pushed it all into one semester, and it was a lot of work. I think I was working about 40-hour work weeks on that, but all unpaid because it was through a class. But um, a mixture of that senior design class and that hands-on experience with my internship experiences where I worked on more projects that were quicker turnarounds, so probably about 5 months long. Um, it's kind of interesting to see like both of those different sides come together. And it's very different than if I'm taking like the intro to land development class or the intro to water resources class, because now I'm actually using the knowledge I learned in those classes to design this petting zoo. And I know some people who did industrial warehouses, people who did apartment complexes, and it's just the culmination of a lot of different things that you need to learn.
Those are great answers. All right, I have one other question for you both. And Annie, this may be something right up your alley with your work in AI. A school called Alpharetta High School in Georgia has asked, how is AI changing the way we measure or create sounds?
Yeah, well, I think in a very general like way to look at how AI is changing anything. It's the idea that we have all this data and we're going to analyze the data in a much more efficient manner, right? I think that's one thing that AI is really, really good at. So sound is something, as you guys have seen, is very, very easy to measure. And although you guys might just have seen decibel version of it, there's so many ways to measure sound, right? You can think about like the different parts of a song. There's the bass, there's like, different levels there, they're all compacted together. We're able to take those apart. And so if you have all this data, with using AI, it's a way to analyze it on all these different fronts. So from that standpoint, like I think it's affecting the way that sound is created, just the way that's affecting, how you guys might use it to, I don't know, like plan your next vacation, right? It's taking all this large amounts of data and depending on what you want to do with it, going through these models, going through, past history and however the model is generating answers, it's going to kind of give you the suggestion. I think another way that relates to maybe something like noise pollution is by looking at like how different factors throughout the day, throughout different environments are creating noise. So I think, one big obvious factor of noise pollution is like traffic, right? And traffic, especially if you ever go visit New York City, it's just like honking, 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 and it's extremely disruptive to not only people but animals, just the entire environment. And so one way that AI could potentially, I guess, resolve this issue better is perhaps looking at the way that cars are flowing in and out of traffic and how that relates to traffic lights, for example, right? So maybe perhaps like, it'll recognize that if the traffic, if the yellow light only lasts for 5 seconds, people are going to, honk a lot more. Maybe that's something it'll realize. Maybe it'll realize like, more efficient way to move people around is through turning on the red light after 30 seconds of green light, something like that. And that'll decrease the amount of engine starting or the amount of honking. That's just one example, but you can imagine how you can apply that to a larger scale with other factors other than just traffic. But I don't know if Morgan, you've any other ideas of how AI would affect that?
I think that AI is definitely really important to use during traffic, but I know that a lot of the times I've seen AI in civil engineering, it's been more on the um more construction side. So seeing if like intuitionally will a person understand like this project. So seeing like like AI obviously understands it in a matter of seconds, but would the typical person without an engineering degree be able to kind of analyze this and be able to like look at this building and kind of know where to go or know if like this is broken or like I haven't really seen it much in my field. I have seen it in transportation engineering, but when I took that class, and that was my only experience with transportation engineering because I don't I don't love that field. I That was before AI came around, or like before AI became really prevalent more at the college level.
Those are some great ideas about why or how we could use AI. I also wanted to highlight, I know there are several schools that were affected by weather and some that are maybe out on their lunch break right now. So I wanted to highlight a few of the designs that some of the other students were working on. You can see a few here in Dr. Holman's class, as well as Academy Charter. You can see the students working on creating their circuits over here and then building their different acoustic panels. So I did want to give a shout out to all these students as well. So up on the screen, if you are enjoying this lab, you may really find yourself trying to figure out like, how do I get into these roles of engineering? So there's definitely different ways that you can do it. You can go as an entry level role, just getting your high school diploma and working in the sound industry. There are certain online programs and trade school apprenticeships that you can do. And you might want to start out there. And then if you really are loving it and finding, just like Annie was saying, trying some new things out. And if you're really loving it, you can always switch over to a four-year university if that's something you're interested in. And maybe you might really love it and decide, hey, I want to go and get my master's degree and work in that way as well. I'm gonna let Morgan and Annie give you some tips on how to get started right away.
Yeah, so as I mentioned earlier, I am a member of American Society of Civil Engineers, and that is over here on the left side. You can see different organizations to get involved in. These are specifically for sound and acoustics engineering, and a lot of times these organizations will have a um, group on campus where you can actually go and network with other sound engineers, other acoustic engineers. And I know, at least for my chapter of American Society of Civil Engineers, we'll bring in professionals to come in and talk about what they're doing, what work they're up to, what kind of field they're part of. And they will oftentimes offer you a job if you just are involved. If you seem interested, they'll be like, hey, want to come and intern with us? And it's really interesting to see, and it's great to network. And I know that I am planning on being a member of ASE for the rest of my career. I'm currently part of the Maryland section as well, and it's really nice to kind of enter a room and everybody just wants to kind of talk to you, see what you're doing, but also like you can see what other people in your career are doing as well. So there's also Society of Women Engineers, and I am a member of that as well. So it's a lot of opportunities just to network with both other students, the faculty involved, and also professionals in the career. Annie, do you want to talk about internships?
Yeah, I think you touched on it. Like, I think in high school it might be a little more difficult to get involved with something specifically related to sound and acoustics unless you happen to, I guess, meet people who are in this field. I don't enter a building that is dealing with this. But very generally, like when it comes to engineering, or any internship that you might be interested in, um, I think the biggest way is really number one, like asking around, right? Like use your connections that you might just have at your disposal. If you know adults who are in some sort of engineering field, just ask them, like, can I shadow you even, if they can't take on an intern. Um, I think so using your network, school, at home, friends, whatever, is one big way. But I think the maybe more formal way, let's say internships, it'll maybe be a little bit more difficult if you don't live in a big city or town to be hands-on with it, but there are virtual opportunities as well, right? Like one of the great benefits of COVID was that we have so many virtual things like Engineering Tomorrow, and you can do a lot of things online now. And whether that's studying by yourself or even finding these remote internships, and even if they're not remote, right? Like there are a lot of in-person ones over the summers that you can apply to. Maybe a little bit harder to get, but still 100%, worth trying. And those, they'll probably like fly you out to do it. They'll cover your housing, and it's just an entirely like new freedom experience you get to have before you even, leave home potentially for college if you do. Um, so highly recommend like trying to get involved in internships. But again, like if you can even just get involved in your own high school, doing clubs, doing extracurriculars, starting your own clubs, like that in itself is something you can't, over exaggerate the impact it has on you, whether it's, not only for your like diligence, your ability to kind of make things up for yourself, college applications, but also just for your interest, right? Like you don't know what you're interested in until you try it. Like I think that's a very general thing you guys should keep in mind. Even if you think engineering is it, for example, try out business, try out law, try out writing or art or something, and maybe you'll realize you're more interested in that than engineering, and vice versa, right? So getting involved is truly like the best way you're gonna set yourself up in your future.
I
Wow.
also think just showing some interest, kind of Annie said like to ask, your parents, ask your friends, ask your family friends if they know anybody who is an engineer. And if you show interest as a high schooler, maybe they won't be able to take you on as an intern. Maybe you won't be allowed to shadow them. But since you did like reach out to them and you showed interest from the beginning, they'll remember you for years to come. So maybe like reach out now and wait a couple years and you'll be old enough that they can actually take you on to work with.
Those are some amazing nuggets. Morgan and Annie, thank you so much for sharing your wisdom about how to get these students involved. It has been such an honor to be here with you today. I think we're ready. I believe Ola, our keynote speaker, is here. Is that correct, Jillian?
Yep.
Yes.
Yes,
I am.
awesome.
Yeah.
All right. Well, let me introduce Ola Jagadi. He is a senior aerodynamicist with Mercedes Formula One. He holds aerospace engineering degrees and not only his engineering degree, but the PhD in supersonic aerodynamics. Both of these from the University of Manchester. What I think is super cool, as being a space person myself, he has worked at JAXA, our Japanese aerospace agency, working on planetary re-entry vehicle design, rocket launches, and language learning. I love that you include that, Ola, because I think it's underrated just how much we have to communicate with people across the world these days. And lastly, Ola is a senior aerodynamicist with Mercedes-Benz Formula One team. He works to design the race car in order to travel as fast as possible and win races. Boy, you guys are in for a treat. Ola, welcome, and thank you so much for joining us today.
Awesome. Well, thank you very much for having me. I've just sent a request to share my screen, if that's okay. Now, just to share the presentation.
Absolutely.
Great. So hopefully you guys can all see my presentation here. I'll move this to the side. Great. Yes. So my name's Olasayinda Jegede. I'm a senior aerodynamicist at the Mercedes Formula One team. And today I'll be giving you a little introduction of acoustics and aerodynamics, which is my personal field. So trying to see where that intersection really lies and how varied the role of acoustics actually is. So let's get on. So who am I? So I did an undergraduate degree in aerospace engineering. I did that mainly because I thought aerospace engineering sounded cool. So I don't know if those are great motivations, but you can definitely have that as well. The picture on, let me point to option. The picture over here is actually me graduating from my undergraduate degree with all my undergraduate friends. So this was an amazing day. And that was from the University of Manchester. And then afterwards, I stayed on to do a PhD. So this picture here is one of the projects I worked on during my PhD, and that was a RC drone, RC UAV. And this was just something that me and some friends at university decided that wouldn't it be cool to be able to have our own platform that we can develop our own technology on and show that it works rather than, trying to strap in a pilot and all the danger that comes with that. So we just started building, and this project came to be because of that, and it was a really fun one. After I finished at university, I then moved to Japan, and that was when I did my stint at the Japanese Aerospace Agency, like was introduced just now, and it was a really fun time. I mean, I had a lot of fun learning language, enjoying time meeting people from different cultures, but also working on spacecraft stuff. So this image here is me at the high enthalpy shock tunnel that JAXA have, and this basically looks at going hypersonic. So today I'll talk a bit about supersonic, but this was going even further than that, and hopefully you'll get what I'm talking about a little bit later on. So this was a real cool experience for me. This picture on the right was one of the experiments that I did whilst I was still in Japan, and it was still with spacecraft. And what we did was we strapped a model of a spacecraft that we'd been developing to one of these atmospheric balloons, allowed the atmospheric balloon to take the spacecraft model up into really high altitude, and then we just dropped it from that high altitude. So we fitted this with lots of like measurement devices and instrumentation so that when the model dropped to the ground, we could actually model how it fell, just as if it was actually entering, Mars's atmosphere or coming back to Earth. So that was also a really fun project. After that, I came to the UK, and that's where I currently am. You can probably guess from my English accent. And I joined the Mercedes Formula One team. And this picture is actually from my first year with the team, where we won my first world championship with the team. And since then, I've gone on to win 3 more world championships in Formula One. So I recognize that I'm speaking to a mainly American crowd here. So F1 has taken off really since the early 1900s in Europe, but in the States, it's still a growing sport. So I'm going to introduce what F1 is, talk about what aerodynamicists do, myself, and how we work, and hopefully you'll enjoy that as well. So what is F1? So I've got a video here from Donut Media on YouTube. If you like it, you can find their stuff online. It's really great stuff, but I think he explains it better than I can. So I'll just hit play on this and hopefully you can hear the sound as well.
It's the most prestigious racing series in the entire world. It's the pinnacle of speed, power, and skill. The most advanced cars on the planet, driven by the most skilled racers, period. The drivers are going 100 miles an hour faster than planes taking off. It's the world's top manufacturers fighting on the most glamorous circuits to see who can build the best race car in the galaxy.
Yeah, I just really like how over the top this guy is, but he perfectly explains it. And essentially what it is, it's about 10 teams. It's going up to 11 soon, and they're all competing to develop the fastest race car. And within that development of the fastest race car, you have 20 drivers who each get to have their own car, and basically they're just racing against each other. So like we say, it's the fastest racing formula there is. The top speed that we've clocked in a race is 231 miles per hour. I think that's actually ridiculous. I don't know if any of you ever had a chance to drive yet, or you've definitely been driven around. And in the UK, the speed limit is 70 miles per hour. So imagine going 231 miles per hour. That's more than 3 times greater than that. So it's completely ridiculous. The next thing is this clip. This is my favorite battle I've seen on screen. So I thought I'd just share this because I have an opportunity to, and hopefully some of you guys start to like F1 too. So here we've got us.
Could be quite vulnerable, not just to Perez, but to Hamilton too.
So this is our car here. This is Red Bull Racing, and this is Ferrari's car.
Towards top corner at 165 miles an hour. Through goes the Ferrari, through goes the Mercedes. So Perez will have a great chance down Hanger Straight into Stoke Corner. Leclerc is beginning to warm up those used hard compound tyres. If Perez can get a good release off of Becker's, he'll get the slipstream, and he's got the DRS. We saw the rear wing open. This is going to be very close into Stoke Corner. Yeah, Perez is catching Charles Leclerc and chasing towards the inside. Perez on the inside. Charles Leclerc gives him just enough space. Can Perez squeeze past and go wheel to wheel towards Vale now? Who's going to be last on the brakes? Leclerc has that inside line. Through goes Hamilton.
Crowds as well. It's amazing.
Perez comes up the inside. He's taking the place back. Hamilton hangs it out around the outside. He's run out of road. Leclerc's still in the hunt as well. So Leclerc trying to get that place back from Hamilton. He has. Hamilton was forced off the track. I wonder what will be said about that. But goes through Charles Leclerc, who's got DRS to pull away from Lewis Hamilton, and arriving on the scene. Well, of course he is. Fernando Alonso and Lando Norris as well. 5 cars separated by about 20 meters here. Perez goes through. Hamilton gets just blocked a little bit by Leclerc. Here comes Fernando Alonso down towards Cox. Hamilton had to get out of the throttle. He was pushed to the outside there, and Alonso then couldn't make anything of that. And off we go again. Absolutely extraordinary.
So yeah, that was one of my most favorite racing clips. And one of the things that we really do appreciate in Formula One is the sound of the engines. Like this, we have our amazing engines that allow us to get to these high speeds, but the crowd also love to be able to hear the cars zoom past. So there's actually been lots of different projects in the past to how do we exaggerate the sound, or how do we make it more pleasing to the viewer. So there's a lot of acoustic work and sound engineering that go on in an F1 race. So my last video for a while, I really like videos, as you can probably tell, is this one, and this is the world pit stop record. So in the UK, we have to service our car every year by law, and sometimes also you've got, you know, flat tires and you have to take them into a garage to be fixed. This normally takes me all day, but when I watch this clip, I'm like, what are they doing? Like, if the people can do it this quickly. That's it. 1.8 seconds to change all four wheels of a car.
Oh, well, that's some incredible teamwork there. Holy smokes.
Exactly. So many people just working together. And the bit I like most about this clip is right at the end you see the other team looking, and this guy's like, that was slick. And sure enough it was. All right, that's videos over for a bit more stats about F1, and then we'll get into some of the meat. So 2.6 seconds to accelerate from 0 to 60 miles per hour, which is mind-bending in terms of acceleration. In terms of deceleration, when they press the brakes, we've got 5G deceleration. Now, if you think about an astronaut taking off to space, that's between 3 to 6G sustained force on the body, whilst drivers are experiencing this whilst racing at these mega speeds and having to make split seconds decisions whether or not they go on the attack or the defense or they play strategically. So they're doing that all at the same time. And then this final stat is what my kind of work is more focused towards, which is aerodynamic downforce. And this basically, I'll talk about it a bit later, but it means 3G, 3 times your body weight. So we create a force that's 3 times the body weight, which can allow you to grip the track and allow you to stay planted as you go around corners really fast, or do other cool stuff, as we'll see. So what is aerodynamics? Aerodynamics is basically the study of how air interacts with solid objects. And these objects can be anything between an aircraft, a car, a bicycle, even buildings. We have to think about the aerodynamics around buildings as well. And our job as aerodynamicists is to improve the design of these objects so that they have ultimate performance, whether that's going fast or being very quiet or yeah, just being the most efficient for what we're trying to do. In terms of the kind of way we work, we focus on 4 main forces. We've got the kind of thrust force, like the engines that propel you forward. We've got drag, that kind of the frictional force that pulls you backwards. You've got the weight of your vehicle, and you've also got the lift. So like in an aircraft, that lift is what's going to keep you in the air. And the way I work on a daily basis is I take a look at our race car, I look at the simulations, and I think, what can we do to make this car faster, better, and just hopefully win races? When I come up with an idea, then we take it to computer-aided design, and we model those. We basically get that idea from my mind onto a 3D model. And then from that, we can run simulations of that just to get an estimation of how that actually works. It's not real, as in it's not 100% exactly what you get in real life because of all models being approximations, but we use this tool called computational fluid dynamics to get a best guess of what might be good. Once we get an idea of what might be good, we then manufacture it. So we're normally using 3D printers. We have like plastic versions of it, or we might even go to the machine shop and get something cut out of metal, just so that we have a version of what we've designed, and then we take that to the wind tunnel. So this picture here is the wind tunnel that we have just over there, like behind the camera for you guys at my base here. And we use that to test how that part that we designed behaves. This short clip just gives you an idea of what a wind tunnel is, and it's essentially just a big fan. The big fan blows air over the model, and then from that we can track how the air is interacting with it, and we can use all our sensors on the car to see if it's an improvement or not. And then once we've done that whole process and we find out that, okay, what we've designed is good, we then send it to the race car, and then hopefully we'll use that to win races, and then we can all celebrate because we've done a good job. I mentioned earlier that as F1 designer, we focus on downforce. And that's basically the same as how aircraft produce lift to keep them up in the sky. But we just flip that whole idea upside down so that we create a force that plants us down into the road. And the stat I said earlier was 3 times your weight, which basically means if you're able to create a force 3 times your weight, you could actually drive your car upside down. An F1 car creates enough downforce that it could drive on the ceiling of a building or a tunnel if you wanted. And that's just crazy as well. So enough aerodynamics. What will we talk about today? You guys came to hear about acoustics. So I'm just going to discuss some of the intersections between acoustics and aerodynamics in a few really prominent ways, but there's plenty more as well. Some basics. I'm sure you guys covered this in your workshops earlier today, but these are just the basics that will help you understand what I'm going to talk about later. So sound is a form of mechanical wave, and it's basically from the vibration of particles. Example of this is this kind of speaker diaphragm that's vibrating forward and backwards. If you were to imagine the air particles that are next to this vibrating diaphragm, you can see that those particles are being pushed side to side, and that pressure from that diaphragm knocks into the particles, which then knock into the next particle, which then knocks into the next particle. And if you were to track just the motion of this kind of pressure wave being distributed or translated, it's being, it propagates throughout the field. But if you were to look at just one single air particle, it's just moving forward and back, forward and back, forward and back. And that's what we call kind of pressure waves propagating. We call that sound. When these vibrations eventually reach our ears, our mind does some fancy stuff to interpret them, and that's how we hear sound. The final thing I just want to point out on this slide is that this kind of propagation of sound waves or pressure waves, it has a speed, and that speed depends on the temperature. But for example, in air at normal room temperature, it's about 343 miles per second, meters per second, or 767 miles per hour. And then the final thing here is that although these two examples are shown in 2D, this is actually a really 3D phenomenon. So if you had a sound source right at the center, this pressure wave would expand and distribute the room eventually in a full 3D spherical way. So supersonic aerodynamics. These little animations below took ages to do on PowerPoint. PowerPoint isn't the tool to use for this, in case anybody ever wanted to do this again. But imagine you were a person stood in the center of a room, or imagine I'm here as I am talking. If you were to track the kind of wavefronts of me making sound, you can kind of see how the sound spreads further and further out, kind of what we saw in the previous slide. Now, if I took a snapshot of just what we saw now, and we looked at that, and we stopped it just at any moment in time, we can see where the kind of sound propagates to in different, over time. If you were stood over here, you'd be able to hear me because the sound's propagated to you. If you stood in front of me, you'd be able to hear me. If you stood behind me, you'd be able to hear me. If you stood over here, you'd be able to hear me. And I'm sure we're all quite familiar with this. We stood in a room talking to somebody. That's how we hear people. Now, if you imagine that the thing that's creating the sound is moving. So here I've got a little example of an airplane, but you can imagine that airplane has some very loud engine noise. So it's creating noise, but it's also moving as well. Then you get something that's slightly different from what we just saw. So I'll play this clip. You can see now the pressure waves are still being generated at the same frequency and the same pulse that we saw in the previous slide. But as the aircraft moves, these waves just start to bunch up together towards this end, whilst they just get more and more further apart behind. If we were to once again take a snapshot of what we're seeing here, what we'd see is something that looks something like this. And this is actually quite interesting little diagram, because you can still start to understand how we're moving towards what we end up calling supersonic. So this aircraft is moving quite slow. And if you were somebody stood over here, the sound of this aircraft would have got to you. So you can hear that the aircraft was there. Over here, the same. Over here, you're starting to see the pressure waves starting to increase in frequency. So I'm sure you guys have studied about bit already today about the Doppler effect, but this is also another way to express that. And then finally, if you were stood right in front of the aircraft, you'd be able to hear it. If your eyes were closed, you'd hear something, and then you'd open it up and you'd see that there's an aircraft coming toward you. And this is all what we call subsonic. Now, what happens if the aircraft is moving really fast, right? And this hopefully gives you an idea. You've still got the same rhythmic propagation of these pressure waves, right? But now you're going fast enough that they're kind of leaving the sound behind. And this is what we call, when you're going faster than the speed that the sound propagates, this is what we call supersonic flight. If we were to take a snapshot of what we just saw, you've got all these pressure wave fronts actually falling behind the aircraft. And what we regularly do is we draw a line, and this is an imaginary line, but it just basically illustrates what we call the Mach cone. And what you see is on this side of this Mach cone, you've got all the pressure waves. So sound has got to this area, whilst on this side, none of the pressure waves have got there. So there's no sound that's been transmitted there. And it's quite funky when you start thinking about this, because if you stood here, you'd be able to hear that the aircraft was there a while back. If you stood here, you'd be able to hear it. But if you stood here, the aircraft's already passed you, but you can't still hear it. You still have no idea that the aircraft has gone past you. And that's one of the funny ways that supersonic aerodynamics aerodynamics and acoustic really like intersect this kind of phenomenon of what we call this quiescent region, which is basically the silent region. And even if you were stood right in front of the aircraft, you wouldn't be able to hear a thing. You might be able to see it, and you're like, what's that coming to me? But you wouldn't be able to hear a thing. So I think that's quite wild. Now, two more little thought experiments. Imagine this aircraft was moving across the screen at that speed, at supersonic speed, but you were also moving at that supersonic speed. So for all this time, you were still staying in this quiet, silent region. So you would never be able to hear that there's an aircraft that was right in front of you, even though it's right next to you. But in reality, we are normally, sat on the ground and maybe an aircraft flies overhead. So what actually happens is eventually that, we move out of the silent region and into the Mach cone. So we actually eventually get to hear the sound of the aircraft. And usually when we hear that, it comes in the form of what we call a sonic boom, this really loud sound from all the information of the pressure waves basically coming at the same time. And we can see this in actual live videos. And I really like this video because you can hear how silent it is as the aircraft flies by at supersonic speeds. But then all of a sudden, well, I'll let you listen to it. I'll play that once more, but notice how the aircraft is already somewhere over here before all of a sudden you hear the sound of the boom, the sonic boom. And some of you may have actually seen in the news recently, there's been a new company called Boom, who have made a lot of progress on trying to reduce the sonic boom because it's actually a really big problem. It's one of the reasons why supersonic travel has been kind of left behind because of this noise pollution problem. We have to figure out how we can, have a plane flying supersonic speeds, but not disturb everybody at nighttime or keep people awake or suddenly shock them as a sonic boom occurs. So this new company called Boom have figured out a way to refract the sound waves away from, the people who below who would be able to hear it. And, if you go into a career in acoustics, maybe you'll be working on projects like this and trying to figure out this kind of supersonic acoustic problem. So yeah, definitely take a look at them if you're interested. They're doing really fun stuff. The next project I'll talk about is the Thrust SSC. And SSC stands for Supersonic Car. And this was designed in 1997 by a group of really crazy British people. Like genuinely, you must be a little bit crazy to decide that actually I want to beat the speed of sound on a car, like in a land vehicle. And essentially what it was this car, or maybe I should just call it like a land rocket, because they literally had two jet engines strapped to this vehicle, and they did actually break the sound barrier. So I'll play this video from 1997. I apologize, it's like 240p on recorded on a toaster, but that's what we had back then. And just listen out for when the sound barrier is broken. This is my favorite bit. So that was them celebrating at the end, knowing that they'd beaten the land speed record and broken the sound barrier. But yeah, so I meant to say, listen out for the sonic boom, and you could see how happy those guys were when all of a sudden the car went past, and you wait a few seconds, and then you hear the sonic boom. That told them already that they broke that barrier. So really great news. And if any of you find this project interesting, they've actually followed it up with what they're calling the Bloodhound SSC, and they're trying to go to 1,000 miles per hour on land. And that project is going on right now, and it'll be going on for the next few years. So maybe in the future, some of you guys will be working on this Bloodhound project and going ridiculous speeds as well. Cool. So this is kind of like my last main slide on the interaction between F1 acoustics and aerodynamics. But I mentioned earlier that one of the best things about F1 is the sound of the engines and the racing. And one of the things that we have to consider is that this is actually really loud and it can be a hindrance. So I actually got this story from one of my old colleagues called Gabe Elias, and he did a lot of this work. And basically what happened was in 2020, we were thinking of expanding the Formula One calendar to Miami. So there, up to that point, there was a race in Texas, but F1 likes to go everywhere. So we have races in Europe, we have races in South America, we have races in Asia, but we wanted one more race in Miami. And when that was proposed, the idea of having a race in Miami got heavily put down, mainly because the residents there were worried about the noise, the sound levels that would come with it. And this image here actually is the official complaint that was submitted in Miami, because they were worried that it would get too loud and it would ruin, their personal happiness or personal ability to sleep, which is a genuine worry and fear, and understandable. This picture up here shows Silverstone, which is one of the tracks we have in the UK. And this black line is the track itself. And you can kind of see this row of little boxes, and these boxes are actually houses. So you can actually see at times the houses are really close to the track. And if you remember from how loud these vehicles are, could be no joke. So what my friend did at that time was he went for a race weekend. He set up some measurement equipment, some microphones, and measured the decibel levels that were recorded from the racing that happened. And through this, we were able to show the kind of peak sound volumes, the regularity of the sound, and basically just alleviate a lot of the concerns that people had about how loud it was going to be. And because of this kind of acoustic engineering work that got undertaken, we were able to get the approval that we needed. And in 2022, we hosted the first Miami Grand Prix, and just under 250,000 people were able to show up and have a great time. And since then, they've added the Las Vegas Grand Prix. So we've been able to spread more around the US also, just because of really good acoustic engineering work. So that kind of sums up my whole presentation on acoustics and the intersection with aerodynamics. This last slide is just about kind of where some hopefully helpful ideas when thinking about how to pick careers and how to go about it. And the thing I'd probably recommend the most is that you just, follow the things that you're most interested in. Like, if you're interested in F1, like from some of the videos, hopefully you're interested in some of the videos I showed you, then watch more about F1. And if you then start to find a particular area of F1, whether it's the aerodynamics or it's the mechanical side or it's the electronic side of it, and if those kind of throw up questions like, how does that work? Or why do they do it that way? Follow those questions. And if it's not F1, like, even if it's like, oh, I really like that song I heard, and why did I like that song that I heard? And is it because of, the use of lyrics there? Maybe it's the poetic nature. Like, what are the questions that are driving you? And then after you have those kind of like ideas of what things you find interesting, then decide on what education you need to follow that. So if then okay, I want to become a mechanic, or I want to become an electrical engineer, then you already know what you want to study, right? You want to study electrical engineering at university. And then to make it a bit more specific from my experience, if you do want to follow into engineering, especially like F1 engineering and aerodynamics, then the things that you're going to need are usually pretty obvious, I guess, and that's maths, because there's a lot of equations, there's a lot of calculations that do need to be done, and physics. Like, you guys, if you were able to follow with my bad explanation today, then you've already really used your physics knowledge to understand how we go from slow speed to subsonic, to low subsonic speed to high subsonic speed, to actually breaking that sound barrier. That's a physics concept, right? So we do a lot of those kind of things, and just being able to have the ability to grasp those kind of concepts is really key. But then you get to like the three soft skills, I would say, where it's the practical thinking. In Formula One, we get a rule book given to us, and things like your car can't be bigger than this, and it can't be smaller than this, it can't be wider than this, it can't be heavier than this. So we get like the parameters we have to play within, but then it's up to us to think, okay, how can I use this to the maximum degree? So a lot of practical thinking, and also we live on planet Earth, so there's constraints, whether that's time that a project needs to take, or money, or whatever it is. So just having those kind of practical thinking and project management aspects is really helpful. And then personally, I think this is a really important thing, and that's creativity. And yes, creativity is usually when people are talking about being able to make music or do great pieces of art, but we actually also need a lot of creativity as engineers to just look at a problem and figure out the best solution for it. And I think that's what actually separates a lot of good engineers from great engineers. Yeah, so those are the skills and also background that I think would help if you wanted to also go into F1.
Well, I love that you included creativity and practical thinking, because I think that is so true, whether it's in engineering or any other degree, like having those skills are so important. All right, we have a question for you, Ola. Question from Challenge Prep. How is a driver's hearing protected during races, and do the helmets have soundproofing?
Yeah, so the drivers actually have specially molded in-ear earplugs, and they're specially molded because, one, they have to take like the shape. Everyone's ears are slightly different shaped inside, so one, they do that, but two, also to only permit specific frequencies from being able to enter. And you can actually buy these personally for yourself. So I've got like my own special earplugs, and they block out like loud droning noises and really high pitched noises, but they also allow frequencies like regular human talking, so that you can still have a good conversation, but if anything too loud comes in the way, it protects you from that as well. And our drivers have that, plus they also have some connectivity, so that we can talk directly between the pit wall, our engineers, and the driver as well.
That's excellent. Okay, Ola, you have talked so much about teamwork, and I think that is so important in probably every industry as well. But to have everything work correctly with the car, to have the precision of your team to be able to change those tires, tell us, like, how do you pick people to be a member of your engineering team, of your pit crew, of the driver, all of those good things?
Yeah, so it's a really good point. And genuinely, this is a team sport. Like most people only see the drivers go around, but up to get to the point where the drivers even get in the car, there's been over 1,000 people, for example, at Mercedes working on this car, and we're working on 2 cars. But it is, we have this saying at Mercedes, it's everybody brings their own tenth, basically. And it's only a tenth of a second, which is like a microsecond. But when you add it up, it's how we win races. That's how we actually get faster than the other competitions. So we just focus on the processes, the individual processes, and make sure that each person is doing their thing to their utmost possible. In terms of how we pick people, I think it's quite funny. I think there's a lot more of a personal aspect of becoming an engineer than you'd expect. Like, I remember even in my interview, like half of it was technical and the other half was just like soft skills, like just understanding what kind of person you are, how well you work in groups, and how you handle stress and how you handle pressure. And it's just being, I guess, the complete package where you've enjoyed life enough to know how to get on with people and work well in a team. And that's what we need, right? Teamwork. So it's being capable, but it's also being open to working together and knowing that you can't do it by yourself. No one can do it by themselves. So you have to work together hard.
So good. All right, here was another question from some of our students. What role do engineers play in solving some of today's biggest global challenges?
So I'd probably answer that more than just F1, but I'd start with F1. For example, one of our biggest global challenges is climate change. And one of the things that we've been doing as a company, actually as an industry, the whole F1 industry is moving towards more sustainable fuels. So using synthetic fuels, biodegradable, or sorry, fuels with biomaterial content in order to reduce the impact that it's having on the environment. We use quite a lot of power to run our systems, so we use things like wind farms and solar energy. So as an industry, we're just moving towards a scenario where we're being less taxing on Earth. But I think engineers are in actually the perfect place to actually help our future goals. I think one of the things that I think about is one of my friends, he works in like the energy sector, and he was looking at ways that they can store excess energy, because right now we actually have a lot of renewable energy available to us, but it's only available to us during peak sun, well, when the sun's shining or when the wind's blowing. But apart from that, you don't have access to that. So being able to store that electricity when it's available and be able to use it when it's not. And that's an engineering problem. I remember working with him on this project and thinking, I have to come up with a solution. Like, the solutions aren't currently there. So I think, if anything, engineers are in the best place to solve our goals for the future and help us move towards a more sustainable future.
Those are some great answers. And then lastly, you were showing us that, like, not noise violation, but they were worried about the noise and they did all those different sensors testing of how loud that sound was, and were able to prove that it wasn't as damaging or as concerning as they thought. Do you know, are there any AI adjustments that are happening due to AI now that can help us figure out if we should change designs or add different barriers? And is that being used in the industry these days?
So currently in F1, I don't think we've started to look at that, but in terms of just the ability of AI to really help the kind of like acoustic sound engineering world, it's quite clear. Like, for example, with aircraft, we have really loud engines, and there's kind of similar to the noise cancelling earphones that you can get for yourself. But there's a lot of work being put into creating like an anti-sound, so that the sound that you're creating is being cancelled out. And like AI is really helping that process, being able to generate, the waves that would help to cancel out the sound waves that you're trying to block. So there's a lot of really interesting work there. I think that's probably how I'd say AI is helping the acoustics kind of field. AI is immensely helping aerodynamics as well. Like we're looking at models for lots of things, just to, even just doing our simulation work is a really, really important way that AI is able to contribute. And I just know of like, engineering fields where things like in the medical industry, we didn't even touch on it today, but ultrasound is a way that we can use to visualize things that we can't see with our own eyes, and it can actually also be used as a healing therapy, and all those aspects of sound engineering that we've just been doing kind of almost brute force. We can use AI methods to help improve our ability to do them.
Dr. Jaggedy, you have been so incredibly inspiring. I feel so honored to be here with you today, and I'm sure our students do too. I took away a few key nuggets from your presentation. Number one that I took away was that teamwork is key. And I love that you said like everyone gets their 10th, everyone brings the 10th. That is so, so cool. The other thing that you were really inspiring about was following the questions that we're most interested in, the things that we're like most intrigued with, and to let our passions drive our education and not the other way around. Just, oh my goodness, so many good, inspiring nuggets. Thank you so much for being here. I did want to highlight a few of our schools for you to take a look at and see their designs as well. You can see here was Challenge Prep doing their sound barrier, and they had went across their school to find all kinds of different materials they could use. Academy Charter was rocking it out there with Mr. Jerry Dawes. You can see out here, they were able to reduce their sound. It was approximately 20 decibel difference that they were. And lastly, I just love this academy. Back here, believe in yourself. This poster like struck me so hard. And it's exactly what Dr. Jaggedy was getting at too. Find those things that you're curious about. Believe in yourself, because we here at Engineering Tomorrow believe in you, and we cannot wait to see everything that you'll be doing. I'm going to hand it back over to Jillian to give us our final instructions.
Absolutely. Thank you again, Dr. Jaggedy. That was inspirational. I know so many students are going to go home and talk about the guest speaker they had today and now their future goals, right? Thank you to ET staff, to the college mentors, for Betsy Fortman for leading this awesome event. Definitely want to see you back for our next event on April 2nd for remediated sites. Please submit those exit tickets. Thank you, Jen. And look out for an email later today with a recording of today's awesome event. Thank you guys so much for being here, being engaged. And thank you again, Ola. That was so good. You guys have a good one. See you soon.